Hello and welcome to the TI Precision Labs hands-on experiment on noise. In this experiment, we will learn how to calculate, simulate, and measure noise. We will also look at two different amplifier configurations to see the impact that resistor values have on thermal noise. For this lab, we will use the OPA 320 datasheet to do a total RMS noise hand calculation. Then we will simulate the noise for the same OPA 320 circuit using TINASPICE and compare the hand calculation to the simulation. We will also simulate the noise for the REF 6050. Next, we will use the ADS 8860 datasheet to find the converter's RMS noise voltage. The ADC noise, reference noise, and amplifier noise are then combined to find the total system noise. Finally, we will measure the system noise and compare it to the predicted value. The circuit we will analyze and measure is shown here. Two different noise coupon cards will be used to show the effects of changing feedback resistance on noise. The input signal is a DC 0.1 volt precision source. The output is the input multiplied by the gain, which in this case is 0.1 volts times 11 or 1.1 volts. Variations in this DC level are the noise that we will measure. We will separately analyze the amplifier, reference, and data converter to predict the overall noise. Let's take a closer look at the amplifier circuit. This slide shows two different amplifier circuits for which we will calculate, simulate, and measure noise for this hands-on experiment. These two circuits are very similar. Both circuits have the same gain, bandwidth, and output filter. The difference is that the feedback network resistance for noise 1 is scaled to be 100 times larger than for noise 2. Thus, noise 1 will have more thermal noise than noise 2. The objective of this experiment is to learn how to calculate, simulate, and measure noise for an ADC system. Also, we will see how thermal noise from resistor scaling impacts the overall system noise. Here is the noise hand calculation for the Noise 1 coupon board. If you aren't familiar with amplifier noise calculations, please review OpAmp Precision Labs using the link at the bottom of the page. The first part of this calculation finds the bandwidth for the feedback network, the charge bucket connected to the output of the amplifier, and the amplifier gain bandwidth limitation. The bandwidth limit is 1.33 MHz for the feedback limit, 5.81 MHz for the charge bucket filter, and 1.82 MHz for the amplifier gain bandwidth limit. These three poles combine to form a multi-order filter. Since the cutoff of the amplifier and feedback network are close together, we simplify the calculation by approximating the filter as a second-order filter with a cutoff at 1.33 MHz. This will be sufficient to get a ballpark value, and the simulation will give a more accurate result that will account for the exact position of each pole. In the next part of this calculation, we find an equivalent resistance for the feedback network by putting the two resistors in parallel. Then we compute the thermal noise using this resistance, Boltzmann's constant, and the temperature in Kelvin. Next, we combine the OpAmp broadband noise density from the datasheet with the thermal noise. In this example, the thermal noise of 12.23 nanovolts per root hertz is combined with the OpAmp noise of 7 nanovolts per root hertz to yield 14.09 nanovolts per root hertz. Next, we convert the spectral density to RMS noise by multiplying by the square root of the noise bandwidth. Finally, we multiply the RMS input noise by the noise gain to find the output noise. This slide shows the noise calculation for the Noise 2 circuit. This calculation is almost identical to the last one, except that the equivalent feedback resistance is much lower. In this example, RF is 1K and R1 is 100 ohms, so the equivalent parallel combination is 90.9 ohms. The thermal noise for this is 1.22 nanovolts per root hertz, whereas the noise in the last example was 14.09 nanovolts per root hertz. This has a significant impact on the overall noise. The total noise for this example is 99.2 microvolts RMS, whereas the noise for the last example was 196.7 microvolts RMS. Thus, the feedback impedance can have a significant impact on the system noise. In general, system noise can be reduced in the following ways: averaging the signal, reducing bandwidth, reducing resistances that generate thermal noise, and selecting an amplifier with a low noise specification. For more details on reducing total noise, refer to Op-Amp Precision Labs. Simulation can also be used to find total noise for amplifier circuits. This process is much simpler than the hand calculation, so many engineers skip the hand analysis. However, the hand calculation is well worth the effort as it gives you better insight into the origin of noise sources than the simulation does. Furthermore, solving the problem two different ways is a good way to confirm that both the simulation and hand analysis are correct. For example, if your simulation circuit had a wiring error or a model issue, you wouldn't know that you had a problem unless you had a hand calculation to compare your results to. To run the noise analysis in TinaSpice, select Analysis, Noise Analysis from the menu. This will cause a noise analysis window to pop up. Enter a valid frequency range for your circuit. In general, the maximum frequency should be set to about 10 times the bandwidth. This circuit bandwidth is in the megahertz, so a frequency range from 1 to 100 megahertz is appropriate. Select the output noise and total noise diagrams. Output noise is the noise spectral density measured in volts per root hertz. Total noise is the integrated RMS noise. The point at the end of the total noise curve where it flattens out or converges to a final value is the integrated total noise that corresponds to the hand calculation. In this case, the hand calculation was 196.7 microvolts RMS, and the simulation gives a total noise of 170.8 microvolts RMS. The discrepancy between the two numbers is because the simulation more accurately accounts for all the poles in the circuit. This slide shows the simulation results for both noise circuits. Note that you can compare two curves in TinaSpice by first selecting and copying the curve. Just click to select the curve and press Ctrl-C to copy. Next, switch to another tab and paste the curve for comparison. Just press Ctrl-V to paste. By looking at the curves, you can see that the noise density and total integrated noise is much lower for the noise 2 circuit. Furthermore, you can see that the bandwidth is approximately the same for both circuits. The bandwidth was intentionally kept the same so that the only variable in this experiment is noise density. To run the simulations, just click on the Tina icon in the PowerPoint presentation. This will open up the Tina files as they are embedded in the PowerPoint. The simulation for reference noise is performed using the same approach as for the amplifier. First, select Analysis, Noise Analysis. Second, enter the frequency range and select the output noise and total noise diagrams. And finally, the point in the total noise curve where the noise converges to a final value is the value used for the total system noise calculation. That is 6.31 microvolts in this example. Now let's use the amplifier and reference noise with the ADC noise to find the total system noise. This slide shows a hand calculation for total system noise. This calculation uses the amplifier and reference noise that we simulated earlier. We also need to get the ADC noise from the datasheet. Unfortunately, most datasheets do not directly specify the noise. Rather, they specify the signal-to-noise ratio. Using the signal-to-noise ratio and the full-scale RMS signal amplitude, we can solve for the noise. First, the full-scale RMS signal is calculated by multiplying the full-scale range by 0.5 and 0.707. The factor of 0.5 translates the peak-to-peak range to peak. The factor of 0.707 converts peak to RMS. In this example, the 5-volt range is translated to an RMS full-scale range of 1.767 volts. Next, the signal-to-noise ratio equation is arranged to solve for noise. The typical SNR given for this device in the datasheet is 93 dB. Plugging in the values, we get a noise of about 39.6 microvolts RMS for this device. Next, add all three noise sources using the square root sum of the squares. For this example, the ADC noise is 39.6 microvolts, the amplifier noise is 180.8 microvolts, and the reference noise is 6.3 microvolts. The combined overall noise is 175.4 microvolts. Now let's take a look at a software tool that can do this calculation. The Analog Engineer's calculator can take the amplifier noise, reference noise, and ADC signal-to-noise ratio and compute the total system noise. The numbers used in this example are the same as in the previous slide. Now that we've done the calculation and simulation, let's set up the hardware and measure the performance. First, set the jumpers on the P-Lab hardware as shown. In this experiment, no external signal source is required as the P-Lab's board has an onboard precision DC source. Next, plug the PHI into the P-Lab's Channel 2 connection and install the OPA 320 Noise 1 coupon board into the Channel 2 socket. Finally, plug the USB cables into your computer. When connecting the USB cable to the computer, an LED on the PHI should blink. Let's pause for a moment to set the jumpers and connect the USB cable. Now let's start the software by selecting the P-Labs SAR EVM icon from the Start All Programs menu. Once the software is running, you should notice the green Hardware Connected message at the bottom of the software. Also, you should notice 3 power LEDs on the P-Labs board illuminate. Pause and start your software. Now we are ready to measure noise. The default sampling rate of 1 megasample per second and the default of 262,144 number of samples works for this experiment. Press Capture and you will see the DC level on the time domain display. Ideally, this would be a flat line at 1.1 volts, but in reality it is an average value of 1.1 volts with a noise signal riding on it. If you look at the maximum and minimum values measured, you can see that the value is approximately 1.1 volts. To get a better understanding of the statistics behind this measurement, change the page to histogram analysis. The histogram analysis page displays a histogram of the data collected in the time domain window. So the mean value of this histogram is 14,541 codes, which corresponds approximately to 1.1 volts. Ideally, we would like to see only one bin in the histogram at 1.1 volts, but in reality we get a Gaussian distribution. This is the expected distribution for a noise signal. The statistical information is very useful for noise measurements. The sigma value is the standard deviation or RMS value of the measured noise. Sigma is given in codes, so to compare to noise in microvolts, we have to multiply by the LSB. The LSB is computed by taking the full-scale voltage range and dividing by 2 to the n, where n is the number of bits. For this example, the full-scale range is 5 volts and the number of bits is 16, so the resolution is 76.29 microvolts. Sigma for this example is measured as 2.18 codes. Multiplying by the LSB gives an RMS noise of 166.3 microvolts for this example. This table summarizes the calculated, simulated, and measured results for this experiment. Your measured results should be close to the example measurements, but you may see some differences. Remember, to translate sigma to an RMS noise voltage, you multiply by the LSB bit width. Comparing the simulated noise to the example measurements shows that the two numbers compare very well. Remember, there are many factors that impact noise, so you should not expect the results to match exactly. Pause now and fill in your measurements. Sometimes it is useful to post-process the data from the EVM. Before copying the data to Excel, let's reduce the number of points to 16,348. Strictly speaking, we don't need to do this, but the processing time for the large data set used previously is long, and the smaller data set is sufficient to illustrate the point. To export the data to Excel, right-click on the graph and select Export, Export Data to Excel. This will open an Excel spreadsheet. To select the data in the Excel spreadsheet, select cell B2 and press Shift, Control, down arrow. This will highlight the cells we want to copy in the spreadsheet. Press Control C to copy the data. Pause and copy the data from the spreadsheet. Next, open the Excel spreadsheet by clicking on the Excel spreadsheet icon in the PowerPoint presentation. This icon is an embedded Excel spreadsheet that will allow us to quickly graph the data and look at the effects of averaging. Next, click on cell B2 and press Ctrl V to paste the data into the raw codes column. After pasting the data, the graph and table will automatically update. This spreadsheet shows the effect of averaging on noise. A rolling average of 10 and 100 is applied to the data. Theoretically, you should see the noise reduced by the square root of the number of samples. In the table, we compare the theoretical noise reduction by averaging to the actual measured averaging. The measured and calculated results for this example are fairly close. In the graph, you can see the averaged noise overlaid on top of the raw noise. Clearly, averaging has a strong impact on reducing the noise. Averaging can be thought of as a simple digital filter. This isn't always a practical way to reduce noise, but it can be useful in some cases. Pause and paste the data into the spreadsheet. That concludes the hands-on experiment. I hope this was useful to you. Thanks for your time.